We're in Rosen, section 1.6, rules of inference. That's Rosen discrete mathematics and its applications. And in this section, we start to finally be able to tackle the mortality of Socrates, because we were going to learn what are called rules of inference. Here's the sections of our, here's the section summary, and we will cover through the rules of inference, so the second bullet in this short briefing. Here's our Socrates example again. How are we going to get to that conclusion? One of the ways that we will construct this is by using this type of structure here. We're going to see this several times where we have premises above the line and a conclusion below the line, and this triple dot is sort of a phrase that means therefore, a symbol that means therefore. So for every x, man x implies mortal x. Socrates is a man, therefore Socrates is mortal. And we'll see the validity of that soon. So we're going to basically show how to construct arguments. Earlier we had done proofs using equivalences. Now we're going to use inference rules, and then we'll be able to extend those to predicate logic and quantifiers as well. Okay, so we've kind of talked about this a little bit. An argument is a sequence of propositions. We call those premises, and we want to come to some kind of valid conclusion using those premises. And we say that the argument is valid if the premises imply the conclusion. And we're going to be using what are called argument forms that are valid no matter what the propositions are. That way we can trust them. If we get the premises right, true, then the conclusion must follow. So an argument with a form with the premises P1 through Pn, and these can be compound propositions. They don't have to be atomic. And the conclusion Q is valid when all of those premises are conjoined together and Q is implied by all of them. If that statement is a tautology, if it's always true, then if we can show P1, P2, all the way through Pn are true, then the truth of Q must follow. Because remember, with an implication, if you have truth on the left of it, you must have truth on the right of it if it's a true implication. And then we're going to look at a number of basic forms called the inference rules that we'll use by names when doing proofs. All right, so here's the first one. The first rule of inference is called modus ponens, and the meaning of this is to affirm the hypothesis. A mode of affirming by affirming the hypothesis. That's what modus ponens means. And basically, it means that if P implies Q is true and P is true, then Q must be true. And it makes sense because P implies Q is an implication. If P is true and the implication is true, Q must be true. There's the corresponding tautology that you can do the truth table on that. You will see that it is always true. You can do that for all of these tautologies. Example, it is snowing is P. I will study discrete math is Q. P implies Q is if it is snowing, then I will study discrete math. It is also given that it is snowing. Therefore, by modus ponens, I will study discrete math. So here were our premises. Here is my conclusion. That's modus ponens. We'll use it a lot. All right, modus tollens is similar. It is the method of proving by denying the consequence. So denying the consequence or the conclusion. So it's the method, it's the mode of proving by denying the consequence. So if P implies Q is true, and I tell you that Q is not true, it must follow that P is not true. And you could also see this by modus tollens, because P implies Q is the same as not Q implies not P by the contrapositive. And there's the corresponding tautology. Again, I recommend you do the truth tables for these to see that these are always true. And here's our example. P is it is snowing, Q is I will study discrete math. P implies Q as if it is snowing, then I will study discrete math. And the other premise is I will not study discrete math. And then I can conclude, therefore, it is not snowing. All right, so that's modus tollens. The next tautology that gives rise to a rule of inference is called the hypothetical syllogism. And you can kind of think of it as a chain of implications. That my two premises are P implies Q and Q implies R. When both of those are true, then P must imply R. That's what we can conclude. And it doesn't necessarily mean R is true. It just means that P minus R, or P implies R, is true. Okay. So we'll continue with our P and Q being it snows and I will study discrete math. We'll add R as the proposition that I will get an A. And my two premises are if it snows, then I will study discrete math. And the second premise is if I study discrete math, I will get an A. And then I can conclude that therefore, if it snows, I will get an A. Does that mean you will get an A? We don't know. But we know that if it snows, you'll get an A because you'll go through the path of studying discrete math. Hypothetical syllogism. A disjunctive syllogism. In this case, we have the premises of a disjunction, P or Q, and then another premise is not P. Well, if P or Q is true, and then we're also told that P is not true, or not P is true, then Q must be true in the disjunction to make the disjunction true. Again, look at the tautology. I recommend doing a truth table for that. So the premise, the P and Q are I will study discrete math and I will study English literature respectively. My premises in my example are I will study discrete math or I will study English literature. And the other premise is I will not study discrete math. And therefore you can conclude that I will study English literature if both of those premises are true. Disjunctive syllogism. Okay, the next rule of inference is addition. And this is very straightforward. It has one premise and one conclusion. P is the premise. I am saying that P is true. Therefore, I can disjoin anything with P and it will remain true because P is true. So P is true, therefore P or Q is true. P is I will study discrete math, Q is I will visit Las Vegas. The premise is I will study discrete math. Therefore, I will study discrete math or I will visit Las Vegas is a true statement. Addition. Simplification. In this case, all we are doing is taking one part of a true conjunction. The premise is P and Q. Therefore, Q. Or I could have picked P. So P is I will study discrete math, Q I will study English literature. The premise is I will study discrete math and English literature. Therefore, I will study discrete math. And this rule of inference is useful for breaking down, pulling out just what you need in order to make your proof, making things smaller. Simplification. Conjunction. This one often gets confused with addition because we are putting two things together in a conjoined fashion. But it is not addition. We're not adding anything to it. We're taking two premises and combining them. So P is true, Q is true, therefore P and Q are true. I will study discrete math, I will study English literature, therefore I will study discrete math and I will study English literature. We can always conjoin two things that are true. And finally, resolution. Resolution is we have two premises that they're all disjunctions. We have the premises not P or R, and the other premise is P or Q. And I can conclude that Q or R is true. Since either P or not P is false, one of Q or R, or both, must be true, but at least one of them must be true. All right, so P is I will study discrete math, R is I will study English literature, Q is I will study databases. And my premises are I will not study discrete math, or I will study English literature. And the second premise, I will study discrete math, or I will study databases. Since we don't know whether P is true or not true, we can conclude, therefore, I will study databases, or I will study English literature. And we don't know which, but we know that one of them at least must be true. And those are the rules of inference.